You've probably had this experience. You're interacting with an AI, and it's just incredible. It's writing poetry, it's debugging code, it's explaining really complex topics, and then, out of nowhere, it says something that is so confidently and yet so spectacularly wrong. And that raises this massive question for all of us. Is the AI actually thinking? Is it reasoning about the world in a way we'd recognize? Or has it just gotten so unbelievably good at mimicking patterns that it can sound like it knows what it's talking about? Well, let's get into it because a group of researchers has found some really ingenious ways to start answering that exact question. So this whole debate really comes down to this core conflict. On one side, you have what we can call surface competence. That's the AI's amazing ability to sound fluent, to sound plausible. But on the other side, there's system comprehension, which is a genuine understanding of how things actually work. Our job today? It's to find the line, that boundary between those two things. Okay, so how in the world do you even begin to test for something like deep understanding versus just a surface-level skill? Well, the key thing to realize is you can't just ask the AI stuff it's probably already seen a million times in its training data. No, to really get to the truth, you have to get creative. You have to design challenges that are totally new. So the real challenge here is to build a test that forces the AI to generalize, to reason from first principles. Researchers have a term for this. They call it an out-of-distribution problem. And all that really means is you're throwing something at the AI that is completely outside its comfort zone, something it's never seen before. It forces the model to actually think, not just pull a familiar-looking answer from its massive memory bank. And one of the most brilliant examples of this comes from a recent research paper. To test if an AI could genuinely reason about physics, these scientists didn't go for some abstract, high-level concept. Nope. They went right back to basics, to a classic problem you probably remember from high school physics class, the pulley system. And the specific concept they were testing was something called mechanical advantage. Now, all that is a number that tells you how much a pulley system helps you out. So if you have a mechanical advantage of 4, it means you only need to use a quarter of the effort to lift a heavy weight. Seems pretty simple, right? But to actually calculate it, you have to understand how all the pieces of the system are working together. But here is what makes this test so incredibly clever. The researchers didn't show the AI a picture of the pulleys. Instead, they gave it the raw code, specifically code in a language called TIGS, that is used to draw the pulley diagrams. Now, this was an absolutely critical move. It forced the AI to build a mental model of the physical structure from a blueprint, not just recognize a visual pattern it had seen before. No cheating allowed. So the stage is set with this really clever code-based test. How did the AIs actually do? Well, in the first couple of studies, the results were, they were surprisingly good. It really seemed like the models had some kind of a real grasp of the physics involved. So in that first study, the models were definitely better than just random guessing at figuring out the mechanical advantage. They even correctly ignored irrelevant stuff like how thick the rope was or how high the ceiling was, and they correctly identified that the number of pulleys was important. But it looked like they were using a bit of a shortcut, a simple heuristic of just counting the pulleys rather than truly simulating the forces at play. Okay, so the AI can count pulleys. Fair enough, but does it actually understand how they're supposed to be connected to work properly? For the next test, the researchers upped the difficulty. They showed the models 2 systems, one that was a perfectly functional pulley and another that was just a jumbled, non-functional mess of punk. And you know what? They absolutely nailed it. I mean, look at this. The models hit over 80% accuracy, which is way, way better than the 50% you'd get from a coin flip. They could easily tell a real working system from a pile of digital junk. So this suggested they had some kind of a gestalt understanding of connectedness. But the researchers weren't satisfied. The hardest test was still to come. And this is where it gets really interesting. This brings us to the final and most important stage of the experiment. You see, everything we've looked at so far, it was basically just a warm-up. What happens next is where that line between sounding smart and being right gets exposed in a really dramatic way. The researchers knew that even the last test could potentially be solved with some clever shortcuts, so they designed one final challenge, one that was far more subtle, far trickier, a test that you could only solve if you had a true, deep comprehension of the physics. This time around, they showed the AI two systems that both looked totally plausible. On the surface, they both looked connected up. But here's the twist. In one of them, the rope was arranged in a very specific, subtle way that meant it transferred absolutely no force to the weight. It was a structural dud. The big question was, could the AI spot the fake? And here it is. This chart shows the moment of total collapse. The AI's performance absolutely plummeted to 50.8%, which is statistically the same as just flipping a coin. The models were completely guessing. That earlier shortcut of just looking for connectedness was now totally useless, and the AI had no deeper structural understanding to fall back on. The researchers themselves summed it up perfectly in their paper. They said the models failed to understand the single most important part of a pulley system, how the components are arranged to actually transfer force and lift the weight. So, wow, that pulley test revealed a really critical failure point. But what does this all mean for us, in the real world? For anyone who is building things with AI or relying on it for their work, this isn't just some interesting academic finding. This is a crucial strategic insight into how we need to think about and respect the boundaries of this technology. If you take only one thing away from this whole explainer, let it be this. An AI's incredible ability to generate statistically probable words is not, and I repeat, is not the same thing as having a true structural understanding of how the world actually works. Here's a metaphor that I think just captures this perfectly. An AI might be able to generate a beautiful, poetic description of a bridge, or maybe even a plausible-looking blueprint. Why? Because it's seen thousands of them. But that does not mean it understands the physics of tension and compression that actually keep a real bridge from falling down. So what do we do about it? Well, the great thing about this research is that it gives us a practical playbook for finding that boundary. First, we need to design counterfactual tests, just like that broken pulley, that have plausible but wrong answers. Then, we have to validate the structure of the AI's logic, not just how pretty its output sounds. We've got to test for true generalization, with problems it's never seen. And maybe most importantly, we need to educate our teams and our stakeholders so they understand the critical difference between a confident answer and a correct one. Look, this isn't about saying AI is useless or bad. It's absolutely not. It's about being smart. A smart AI strategy isn't about demanding perfection or waiting for some magical superintelligence. It's about being a detective. It's about finding that exact line where your model's incredible reasoning ability ends and its equally incredible ability to bluff begins. That's not a bug to be fixed. It's a boundary to be mapped and respected. And so that really leaves us all with a final question to take home. Whether you're a developer, a leader at a company, or just someone who's curious about this stuff, the most important question you can ask right now is this. In your world, how are you testing for the difference between sounding smart and actually being right? How do you find that line?